California engineered an impossible river, and now it is breaking, not from an earthquake, not from a flood. A 444-mile-long concrete artery, the single most audacious water project in modern history, is being crushed by the ground it was built on. Right now, a silent, invisible catastrophe is unfolding in the heart of the state. The land itself is sinking. It is a collapse so slow, so vast, it is almost imperceptible. But the damage is not. It has already erased nearly half the aqueduct's capacity in its most critical sections. 44%. Gone. That is not a projection. That is the measured reality today. That is a direct threat to the water supply for 27 million people and the irrigation for 750. 0 acres of farmland that feeds the country. But here is the number they don't tell you. A new projection warns that if this continues, the aqueduct could lose 87% of its ability to move water. Not a shortage, a shutdown. California is staring at the end of its water system. So what does that actually mean for the food on your table, for the water in the taps of Los Angeles? If you find this question urgent, take a moment to leave a comment below with your first reaction to that 87% number. It helps us understand what parts of this crisis are hitting home. And right now, at the beginning of this investigation, I have to ask you to do one thing. A huge number of people who find these deep dives essential forget to subscribe. If you believe this kind of reporting is important and you don't want to miss our next investigation, please take 1 second and hit that subscribe button. It is the single most important way to support this work. Let's begin. The California Aqueduct was never supposed to be just a canal. It was a statement, a declaration of human ingenuity over the limits of geography. It is the spine of the California State Water Project, a system so vast it is difficult to comprehend. It begins in the Sacramento-San Joaquin Delta, a massive estuary where Northern California's rivers converge, and from there it sets out on an impossible journey south. Through the arid flatlands of the Central Valley, and then, in an act of breathtaking engineering, it climbs nearly 0 feet over the Tehachapi Mountains. It does not tunnel through them. It is pumped over them. It is a river, forced uphill. The system is a symphony of canals, pipelines, and 19 pumping plants, all working in concert to deliver water to places nature never intended it to reach. From the San Francisco Bay Area, down through the agricultural heartland of the San Joaquin Valley, and finally to the sprawling urban centers of Southern California. It is the circulatory system for the 5th largest economy on Earth, and the entire thing runs on gravity. For most of its 444-mile length, the aqueduct operates on a gradient so subtle it is almost perfectly flat. Engineers designed it to drop just 2 to 4 feet in elevation for every 10 miles it travels. It is a slope so gentle that the water moves not in a rush, but in a slow, deliberate, inexorable crawl. It is a system of immense power built on the foundation of absolute precision. Every inch of concrete, every angle of the slope, was calculated to work in perfect harmony. It was built in the 1960s, a monument to a future of endless growth, a guarantee carved into the landscape. It was a promise that California could support millions more people, could grow food for the nation, could build cities in a desert, and the water would always be there. It was designed to last for centuries. And yet, less than 50 years after it was completed, its fundamental geometry began to fail. Not because the concrete was weak, not because the design was flawed, but because the very earth it was resting on started to give way. A geological flaw that predated the aqueduct by decades was about to turn this modern marvel into a multi-billion-dollar crisis. The ground was sinking, and it was taking the aqueduct with it. To understand what is happening, you have to look beneath the surface, deep beneath. The Central Valley, particularly the San Joaquin Valley, is not solid ground. It is an ancient basin filled with thousands of feet of sediment washed down from the surrounding mountains over millennia. Within those sediments are layers of fine-grained clay. Think of these clay layers like a series of saturated sponges. They're microscopic pores filled with water that help support the weight of all the land above. For generations, that system was in balance. Then came industrial agriculture. Starting in the 1920s, farmers in the San Joaquin Valley began drilling wells, tapping into the vast underground aquifers to irrigate their crops. When surface water from rivers was plentiful, the pumping was modest. But during California's frequent droughts, when river allocations were cut, the pumps became a lifeline. Farmers began pulling water out of the ground far faster than rainfall could ever replenish it. They were mining water that had been stored underground for thousands of years. And when you pull that much water out of those deep clay layers, the system collapses. The water pressure inside the pores, the very thing holding the clay particles apart, drops. The clay compacts under the immense weight of the earth above it. It is not like a sponge you can resaturate. Once crushed, the microscopic structure is destroyed. The ground surface above permanently sinks. This process is called subsidence, and it is not a small-scale problem. By the time the California Aqueduct was finished in the 1970s, parts of the valley had already sunk by as much as 30 feet. The engineers knew this. They built the aqueduct with extra height on its walls, a buffer they called freeboard, to account for some minor expected settling. They planned for inches. They did not plan for feet. The extreme drought that gripped California from 2013 to 2016 pushed the system past its breaking point. With surface water from the aqueduct and other canals cut to near zero, farmers had no choice. They drilled deeper wells and pumped groundwater with a desperation never seen before. The ground responded. In just 3 years, the land beneath some sections of the aqueduct dropped by nearly 3 feet. For a canal engineered to function on a slope of a few feet over 10 miles, this was a catastrophe. The even, gentle slope was gone. In its place, the sinking ground had created warped, uneven depressions. Broken gravity is what some engineers call it. The aqueduct, designed for water to flow downhill, now had sections where the water was effectively being asked to flow uphill out of a sunken bowl. The water slows. It backs up. It ponds. The once mighty flow of the canal, the lifeblood for 27 million people, is choked off. As of 2023, the California Department of Water Resources officially stated that this subsidence has resulted in a 44% reduction in the aqueduct's conveyance capacity. Nearly half. Gone, not because of a drought starving the source, but because of a geological collapse breaking the delivery system itself. And the danger is not just a reduced flow. As the canal bed sinks, the water level inside rises relative to the concrete walls. That carefully calculated freeboard has disappeared. In some places, the water is now perilously close to the top of the liner. Engineers call this the overtopping threat. A sudden surge of water, a malfunction at a downstream gate, and the canal could overflow its banks. If that happens, the water would rapidly erode the dirt embankments that support the concrete structure, leading to a catastrophic breach. A total failure. The aqueduct was not just sinking, it was becoming fundamentally unstable. At this point, you're probably asking, who is paying for all this damage? Leave a comment with your thoughts. Should it be the farmers, the state, or the cities? This debate is at the heart of the entire crisis. The answer is not simple. The subsidence crisis was not just a geological inevitability. It was driven by an economic one. A fundamental shift in California agriculture turned a manageable problem into an existential threat. For decades, much of the Central Valley was planted with seasonal row crops. Tomatoes, cotton, melons, these crops gave farmers flexibility. During a severe drought, a farmer could choose to fallow a field, to not plant for a season, and wait for the water to return. It was a financial hit, but it was survivable. The land would be there next year. Then, starting in the late 20th century, came the boom in high-value permanent crops. Almonds, and pistachios. Orchards and vineyards that cover hundreds of thousands of acres. Unlike a cotton field, you cannot follow an almond orchard. These are not annual plants. They are 25-year investments. A single missed watering season during a drought doesn't just mean no crop for that year. It means the death of the entire orchard. It means losing decades of investment. This created what agronomists call the permanent crop trap. When the state slashed surface water deliveries from the aqueduct during droughts, farmers with permanent crops were not faced with a choice between profit and loss. They were faced with a choice between pumping groundwater or going bankrupt. They pumped. They had to. The relentless thirst of these permanent crops, especially during the 2013-2016 drought, drove the unprecedented groundwater extraction that in turn accelerated the sinking of the land. In a tragic irony, the very agricultural economy the aqueduct was built to support was now systematically destroying it. The frantic effort to save billions of dollars in almond orchards was causing billions of dollars in damage to the water infrastructure they all depended on. It was a vicious cycle, and every player in it was acting rationally based on their own survival. And if you're finding this breakdown of the economics valuable, please take a moment to hit the like button and consider sharing this video. Spreading awareness about these complex, interconnected problems is a critical first step. Many people think this is just about a lack of rain, but the reality is so much deeper. The physical damage to California's water infrastructure is not theoretical. It is measured, documented, and staggering. While the main California Aqueduct has seen a devastating 44% capacity reduction, it is not the only victim. The network of canals that crisscross the Central Valley is a complex, interconnected system. A failure in one part puts stress on all the others. Take the San Luis Canal. This is a more than 100-mile stretch of the aqueduct that is jointly operated by the state and federal governments. It runs through the heart of the worst subsidence zones. According to recent reports, the San Luis Canal has lost 46% of its design capacity. The numbers are almost identical to the damage on the main aqueduct, because the cause is the same. The ground beneath it is collapsing into a series of basins and choke points. Pumps like the massive Dos Amigos pumping plant now have to work harder, burning more energy just to push water past these sunken sections. But the most dramatic example of this slow-motion disaster is the Friant-Kern Canal. This is another major artery, part of the federal Central Valley Project, designed to deliver water to farms on the east side of the San Joaquin Valley. A critical 33-mile section in its middle has literally sunk into the ground. Jason Phillips, the CEO of the Friant Water Authority, the agency that manages the canal, has been on the front lines of this battle for years. His agency has documented a capacity loss of over 60% in that sunken stretch. 60%. The canal that was supposed to carry 4,000 cubic feet of water per second can now barely manage 1,600. It is so bad that in some places, the canal bottom has bowed down more than 12 feet below its original engineered grade. This is not a maintenance issue. This is a complete structural failure. The state and federal governments are now facing a repair bill that is astronomical. To fix just a 10-mile stretch of the Friant-Kern Canal, Phase 1 of the repair project cost an estimated $326 million. That is over $30 million per mile for a canal that is 152 miles long. You begin to see the scale of the financial hole the state is in. And this is just one canal. The total cost to repair all the subsidence damage to the California Aqueduct is now estimated to be north of $3 billion. This is a crisis being managed by people like Carla Nemeth, the director of the California Department of Water Resources, and Christopher Martin, a key policy advisor for the State Water Project. They are tasked with an impossible job, finding the money to fix a system that is actively being broken by the very people it serves. In January 2022, the state awarded a grant of $29.8 million just to kickstart the Friant-Kern repair work. It was a down payment on a debt that keeps growing. This has created a tense, politically charged standoff. Who should pay this multi-billion-dollar bill? The farmers whose pumping caused the damage? The federal government, which operates part of the system? The state of California, meaning all taxpayers? Or the urban water districts in Southern California? Like the massive metropolitan water district, who depend on the aqueduct for their survival and have the deepest pockets? The Friant Water Authority has been embroiled in contentious lawsuits with local agricultural districts, trying to secure funding for the repairs. Some settlements have been reached, but it highlights the brutal truth: nobody wants to pay for a problem that everyone contributed to. Every time an almond farmer turns on a well during a drought, every time a city dweller in Los Angeles turns on a tap, they are connected to this sinking, breaking system. And the bill is coming due. I know this is the second time I'm asking, but the data we see tells a clear story. For every 1,000 people who watch this far into our documentaries, only about 10 are subscribed. That's a 1% subscription rate. If you are part of the 99% who is finding this valuable but hasn't clicked subscribe yet, please consider doing it now. It sounds small, but for an independent channel, it is the difference between being able to fund the next investigation or not. It genuinely keeps us going. Thank you. The numbers documenting the past damage are unsettling. The numbers projecting the future are apocalyptic. In February of 2026, the Santa Barbara Water Commission held a meeting. They were reviewing the latest models from the Department of Water Resources, and the warning they issued was stark. It cut through all the political noise and technical jargon. Without immediate, multi-billion-dollar funding and aggressive repairs, they warned that the California Aqueduct could lose up to 87% of its capacity by the year 2043. Let that number sink in. 87%. That is not a reduction. That is not a restriction. That is a functional shutdown. That is the end of the aqueduct as a meaningful source of water for Southern California. It means the pipe that delivers water to 27 million people and a multi-billion-dollar agricultural industry is effectively turned off. The year 2043 is not a distant, abstract future. It is less than 2 decades away. Children born today would not have even graduated from college. This is not a worst-case scenario from a climate change model about the distant future. This is the direct, calculated, engineering consequence of the ground continuing to sink at its current measured rate. This is the doomsday clock that people like Jesse Dillon live with every day. He is the program manager for the California Aqueduct Subsidence Program, or CASP, at the DBR. He is the engineer in charge of figuring out how to stop this from happening. In an interview, his assessment was blunt. There are no quick solutions, he said. Everybody's going to need to realize that this is as big a problem as it is. The problem is so big that the state's interim plans sound like desperate battlefield medicine. In May of 2026, DWR officials briefed the Metropolitan Water District of Southern California on their near-term remediation strategy. The plan involves physically raising the concrete liners across 47 miles of the canal in the most critical sunken sections, pools 17, 18, 20, 21, 24, and 31. Imagine the sheer logistical nightmare of that. Trying to perform major construction on the walls of a 400-mile-long canal that needs to stay operational. It is like performing open heart surgery while the patient is running a marathon. And even this massive, expensive effort is just a temporary fix. It is a band-aid. It raises the sides of the canal to prevent it from overflowing. But it does nothing to fix the underlying problem of the choked flow. It does not fix the broken gravity. Matthew Lees, a geophysics researcher who has published critical data on the subsidence, put it simply. The bill for repairing major aqueducts like the Friant-Kern Canal and the California Aqueduct is exceptionally high. A lot of the costs of subsidence aren't well known. The state is throwing billions at fixing the symptoms, because fixing the cause, a century of unsustainable groundwater pumping, is a political and economic problem they still don't know how to solve. The question of who pays is a battle being fought in courtrooms and boardrooms right now. But the 87% projection hangs over every discussion. It is a deadline imposed not by politicians, but by physics. One of the most dangerous misconceptions about this crisis is the idea that nature can fix it. California has experienced a few wet winters recently, with powerful atmospheric rivers dumping record amounts of rain and snow. News reports show reservoirs filling up, and it creates a false sense of security. A belief that the problem is over, that the system has been refilled and reset. That is not how this works. The damage from subsidence is permanent. No amount of record-breaking rain will ever raise the ground back up to its original elevation. You cannot reinflate the earth. When the water was pumped out of those deep clay layers, the structure was crushed. The pore spaces that once held water have been squeezed shut. Forever, the geological sponge is broken, and its ability to store water and support the land is permanently diminished. The wet years can refill the surface reservoirs like Lake Oroville, the aqueduct's main source. They can even begin to replenish the upper layers of the aquifers. But they cannot undo the physical collapse of the ground dozens or hundreds of feet below. The sinking is a one-way street. The state has tried to address the root cause. In 2014, in the middle of a devastating drought, the California legislature passed the Sustainable Groundwater Management Act, or SMA. It was a landmark piece of legislation. For the first time in the state's history, it required local agencies to develop plans to manage their groundwater and bring their basins into balance, to stop taking out more water than goes back in. But SGMA is not a fast-acting solution. It is a slow, bureaucratic, and highly contentious process, with deadlines stretching out for 2 decades. It has turned into a series of bitter conflicts between farmers, local water districts, and the state over who has to cut their water use. While these battles play out, the ground continues to sink, the aqueduct continues to break. SGMA may eventually stop the bleeding, but it may be too late to save the patient. The damage is already done. The multi-billion-dollar repair bill is already on the table, and the fundamental instability of the system is now a permanent feature of California's water reality. Every gallon of water delivered to Los Angeles now has to pass through a warped and broken delivery system. Every almond grown in the Central Valley is connected to this legacy of a sinking landscape. The atmospheric rivers are a temporary reprieve. They are not a cure. The permanent scar is already on the land. This brings us to the final, unsettling question. The same one that must keep engineers like Jesse Dillon and policymakers like Christopher Martin awake at night. Final warning, I promise. But if this story has held your attention, and you believe in supporting independent deep dives into complex issues, please take this moment to subscribe to the channel. It's the single most impactful click you can make, and it ensures we can continue this work. Thank you. The California Aqueduct is a monument to an era of unshakable confidence. A time when engineers believed any problem of geography or scarcity could be solved with enough concrete, steel, and political will. They built a river where there was none. They made a desert bloom on an industrial scale. They enabled the growth of an economic superpower. It was an act of extraordinary ambition and undeniable success. But it was built on a geological fault line that had nothing to do with earthquakes. It was built on top of a system of groundwater depletion that was already in motion. The architects of the aqueduct built a system to deliver water, but they could not control the economic and agricultural forces that would lead to that system's own destruction. 44%, 46%, 60%. These are not just numbers. They are the vital signs of a system in critical condition. 87%. That is the prognosis if the disease is left untreated. The multi-billion-dollar repairs are not a solution. They are a desperate attempt to keep the system alive on life support. They are attacks on a century of unsustainable choices. The story of the California Aqueduct is not just a cautionary tale about a water crisis. It is something deeper. It is the story of a system that has become a victim of its own success. A story about the hidden costs of turning a desert into a global breadbasket. A story about a state that is now in a frantic race to repair its greatest engineering achievement before it sinks completely into the ground. So the real question is not, can they fix the canal? The real question is, have they built the most sophisticated water delivery system in human history only to watch it get swallowed by the very